This is section 3.4, problem number 1. And the main thing to know about this is how a function and its derivative and its second derivative are connected to each other. So first of all, if you know that f is increasing, like if you know you have a function that's increasing, then what that means about the derivative, I'm trying to write increasing. Actually, you know what? Let me type this because, well, I don't have to explain why. Look at my writing, how messy it is. So it's better if I type this, right? So basically, like if a function is increasing, that means its derivative is positive. And if a function is decreasing, that means that its derivative is negative. So f increasing means derivative positive, f decreasing means derivative negative. So what they want you to do, so they want you to know that, and then the idea is to look at this graph and say, right here at this point on this graph, is my function increasing or decreasing? And I know that if I were to be walking on this graph from left to right, I would be going uphill. At this point, I would still be going uphill. And so I would say that right here, my graph f is increasing, which means that my derivative has to be positive. And the way we say positive in mathematics is we say greater than 0. So we know that our f prime has to be greater than 0. So our answer has to be either this one right here or this one. Just like the only possibilities are the ones where f prime is greater than 0. And then to figure out which one of these two is correct, what you're going to do is use how a function is related to its second derivative. And for that has to do with concavity. So we say that f is, when f is concave up, its second derivative is positive. And when f is concave down, its second derivative is negative. So I want to look at my graph, determine if it's concave up or concave down. And so just remember that concave up means the graph kind of looks like it's smiling, and then concave down kind of looks like it's frowning. So we're going to go here. Let me erase this here. So we want to see if at this point, so again, they want us to pay attention to where this point is. At this point, does it look like the graph is smiling or frowning? Does it look concave up or concave down? And to me, it looks like it's concave down right here, right? It's like it's concave down. It has that frowning look, which means, so since it's concave down, f concave down means that f double prime is negative, and we write that by saying less than 0. So the one that has f double prime less than 0 is our answer. And it looks like that one is this one right here. So my answer in this case would get rid of this. And I would mark this one, f prime greater than 0, which means my function's increasing, and f double prime less than 0, which means my function's concave down. And there we go. That's number 1. For number 8, let's see what number 8 is. Let me erase all this. For problem number 8, this one's kind of similar. So it's again asking us to relate a function a function's derivative and its concavity. I shouldn't have erased all that stuff that I just erased, huh? So, so the first part of this, where it's asking us to determine what the sign of f of 4 is, that's basically asking us to look at the y value of this function when x is equal to 4. And so we want to look at this point here. And to me, it looks like that point is on the x-axis. So if we think of the black line, the black horizontal line here as the x-axis, then we would say that, we could say that, and that's what I think they're assuming, that we're assuming. We can say that f of 4 equals 0 because it's on the x-axis. It looks like this is the point 4, 0, which is the same thing as saying f of 4 equals 0. So for this one, for the sign of f of 4, I would say 0 for that. And then for f prime of 4, we're going to use that, what I was talking about earlier, about how when f is increasing, f prime, that means f prime is positive, and when f is decreasing, that means that f prime is negative. And so I'm looking at, I'm gonna erase this point that I've drawn because now we're focused on f prime. And notice that, like, if you, again, imagine walking on this curve from left to right, notice at first you're going downhill, right? But then once, so that means your function's decreasing. But then once you get to the 4, it switches, like it stops going downhill. It's like it reaches a low point and then it starts to go uphill, which means that 4 is at a point where your graph is changing from decreasing to increasing, which means that right here we have a horizontal tangent line. Or in other words, the slope of that tangent line is 0, which means that right here at the 4, at this point right here, our function, our derivative, it looks like is 0. Because again, that's the point where it's the graph switched from decreasing, which means like while it was decreasing, the your f prime is negative, right? Oops, negative. And then while it's increasing, f prime is positive. So to the left of the 4, f prime's negative. To the right of the 4, f prime is positive. So the 4 is where it switches from negative to positive. And so, so we can say that in this case, the f prime of 4, it looks like is equal to 0. Now let's say I look at another graph. Let's see if I can find one that's kind of different. Oh, they're all kind of the same. Oh well, I'll ask for a different question after this one, just so you get a kind of an idea of when it's different, like what that would look like. But let's look at f double prime. So the f double prime part, that one is related to the concavity, what I was talking about earlier, that when f is concave up, that means that f double prime is positive. And when f is concave down, f double prime, and again, concave up, visually kind of looks like a smile. The graph looks like a smile, and concave down, it kind of looks like a frown. So if we go to this graph and we look at what's happening at the 4, it looks like the entire graph is concave up. Like everything that we have, it looks like it's concave up. So I would say that this whole graph is concave up. Like it looks like a smile, just the whole thing, right? Which means that f double prime is positive, and the way we say positive is greater than 0, but how do they say it here? I think they actually just say positive. Yeah, they just say positive. So that's this one. Let's get a similar question. Okay, here's a good one. I mean, just to get a different example and to make sure that the ideas stick. So here's another one. So sine of f of 3. I'm gonna like go ahead and mark my f of 3. I mean my point when x is 3. And once again here it looks like it looks like it's at 0. It's on the x-axis, right? So f of 3 in this case would be 0. That's the y value when x is 3. And then for the sine of f prime of 3, I want to ask myself, is this function, if I'm walking along this curve at the 3, am I going uphill or downhill or neither? And in this case, it looks like I'm going downhill. Like at this 3, I'm going downhill, which means that my f is decreasing there, which means that f prime is negative. When f is decreasing, f prime is negative. So for this one, I would say f prime is negative. And then last of all, for f double prime of 3, we're looking at the concavity. And notice this graph, like notice like kind of from here to here, it looks like the graph is concave down, like the frown. But then from here to here, it looks like it's concave up. And at the 3, it looks like it switches from concave down to concave up, which tells me that the 3 is actually an inflection point, a point where it switches concavity. And so, oops, I didn't mean to yell that, inflection point. That's the point where the graph switches concavity. So because you have that switch, kind of like with the previous problem where the graph switched from, I forget, it switched from decreasing to increasing, and at that point where it switched, f prime was 0. So same thing with concavity, but for f double prime. So if it switches from concave down to concave up, then that means that f double prime is 0. Like at that point, at that 3, the graph's neither concave up nor concave down. It's the moment where it's switching. So for this, we would say that f double prime is equal to 0. Just type that here, f double prime equals 0 at that inflection point. So I hope that helps. And then next, problem number 11 was the next requested problem from this section. So, so we'll just go through this step by step. I like this problem. It says, given this function, 8x cubed plus 12x squared minus 48x, find the first derivative. So we can do that using our differentiation rules. The 3 drops down to the front. 3 times 8 is 24. X, and then we take 1 away from the exponent, plus 24x, because the 2 times 12 is 24, and then minus 48. So there's our first derivative. Then it says, notice that g prime of x equals 0 when x equals 1. So like if we plug in 1 for x, it's saying g prime of x equals 0. So g prime of 1 equals 0. They're basically telling us that the 1 is a critical number. And it says we want to know whether there's a local minimum or local maximum at x equals 1. So we'll use the second derivative test. So it tells us to find the second derivative. So we find the second derivative. 2 times 24 is 48. Like that 2 drops to the front. And we multiply 2 times 24 to get 48. X, we take 1 away from the exponent. So we end up with just x to the first power. And then plus 24. And the derivative of a constant is just 0, so I don't put anything for the 48. And then it says find g double prime of 1, which means I need to plug in 1 for my 40 into my g double prime. So g double prime of 1 is equal to 48 times 1 plus 24. And that equals, what's that? 72, is that right? I don't know if that's right. Let's see. Let us see. Oops. See how we're doing so far. Okay, so far so good. So from here, it says based on the sign of this number, does this mean that the graph is concave up or concave down? So what I wrote in the previous problem, when the second derivative is positive, the graph is concave up. 72 is a positive number, so the graph is concave up. And remember, concave up means that it looks, the graph kind of looks like a smile. So, and then, let me just say, it's concave up because G double prime of 1, which is 72, is positive. So again, if the second derivative is positive, the graph of your function is concave up. And then the reason I drew this, I think it's helpful to have a picture, is because of the last part of this problem. It says based on the concavity, does this mean that there's a local minimum or a local maximum at x equals 1? And notice if you're concave up, then that means that there's a local minimum, not a local maximum, because the idea is that maybe these sides over here just keep growing. We don't know, but right here, there's a local minimum. And that's the second derivative test. It says that if your second derivative is positive at a critical number, then that critical number is happening at a local minimum. And if your second derivative is negative at a critical number, then you have a local maximum at that critical number. So, but here I get to say minimum, and then I'm done. So I hope that helps. Take care. Bye.